Hi, I'm Dave Mueller, retired hydrologist from the U.S. Geological Survey and founder of Genesis Hydrotech. Now that we have evaluated the measured data and made the appropriate adjustments and settings, we are ready to concern ourselves with the portion of the stream that is not measured, the top and bottom and edges. We will begin with the top and bottom extrapolation. The purpose for extrap is to provide the user a correct and efficient method to visually determine the best extrapolation method to use for computing discharge in the unmeasured top and bottom portions of an ADCP discharge measurement. The extrapolation method normalizes the data for depth as a normalized Z value, which is 0 at the stream bed, 1 at the water surface, and a normalized unit discharge. For each ensemble, the discharge is averaged, and then the discharge in each cell is divided by that average. And if you note that the average discharge, which would be 1, is very close to 6/10 of the depth from the water surface, which is often what is collected when using point measurements. The algorithm automatically selects an extrapolation method. It displays the discharge sensitivity. A caution or yellow alert is provided if the average difference in the best 4 methods is greater than 2%. The Extrap tab also allows manual changes. Let's discuss how Extrap selects a fit automatically. The blue shaded dots in the graph are the normalized discharge for each depth cell in the measurement. The darker the blue, the greater the normalized discharge. The normalized Z is divided into 5% layers, and the number of measured depth cells in each layer and the average Z for those depth cells is shown on the table at the left. For each layer, a discharge weighted median is computed and is shown in the black square on the graph. The whiskers on each side of the black square represent 50% of the normalized discharge for that layer. The fit algorithm only uses these median values to determine the best fit. Each median value is given the same weight in the fit algorithm. To avoid excessive influence on the fit layers with few points, those layers with less than 20% of the median number of points in the layers are excluded from the fit and are shown in red on the graph. And you'll notice that we have one point in the top layer and we don't see a red square. However, if we scroll to the right, we find that one point that is way off the rest of the points and would have had substantial influence on the top fit if we had included that point in our fit algorithm. The method used to automatically select a fit is based on empirical analysis and comparisons of the automatic fit to hundreds of measurements by experienced ADCP users. The automatically selected fit is not perfect and should be evaluated visually by the user, which is why the graph is front and center on this tab. I will briefly discuss the steps used to automatically determine the extrapolation fit so that you, as the user, have some idea why the fit was selected. However, remember that you are the final authority and have the ability to manually change the fit. Only the median values are used in the fit algorithm. The 1/6 power law is assumed valid unless the data are sufficient to prove otherwise, using the old adage, innocent until proven guilty. If the number of valid median points is less than 7, the data are considered insufficient to reject the 1/6 power law. For 7 or more valid medians, the optimized exponent for the power fit is computed. The optimized exponent is considered the appropriate exponent for the power fit of the profile if it has a coefficient of determination r squared from the regression that is equal to or greater than 0.8. And The default exponent of 0.1667, representing the 1/6 power, is not contained within the 95% confidence intervals of the optimized exponent. The bottom third of the medians are used in a regression to determine the exponent for the no-slip condition. If the R-squared from the regression of the no-slip condition is greater than 0.8, the no-slip exponent computed from the regression is selected. If the R-squared is not greater than 0.8, the no-slip exponent defaults to 0.1667. Next, the algorithm computes the difference at the water surface between a linear fit of the top 4 measured cells and the best selected power fit of the whole profile. Then the difference in the unit discharge between the power fit and no-slip fit is computed at 1/10 of the normalized depth. Using these data, a constant no-slip fit condition is selected if the top of the power fit doesn't fit the data well, which is defined as the difference in unit discharge at the water surface between the linear fit and the power fit is greater than 10%, and the difference is either positive or the difference of the top measured cell differs from the best selected power fit by more than 5%. A constant no-slip condition is also selected if the bottom of the power fit doesn't fit the data well, defined as the difference between an optimized no-slip fit and the selected best power fit of the whole profile is greater than 10% at the normalized depth of 0.1, and the optimized no-slip fit has an R-squared greater than 0.6. A constant no-slip fit is also selected if the flow is bidirectional, defined as the sign of the unit discharge at the top of the profile is different from the sign of the unit discharge at the bottom of the profile. And finally, the fourth condition where a constant no-slip fit condition is selected is if the profile is C-shaped. This is defined when the sign of the residuals from the best selected power fit for the top and bottom are different than for the middle of the profile, and the combined difference of the top and bottom is greater than 10%. When reviewing and deciding on an appropriate fit, you should look at how well the fit matches the data and include in that evaluation any side information that you have, such as channel shape and wind direction. But you should also look at the sensitivity table to evaluate the percent difference in final discharge that will be made by changing the extrapolation methods. If the change is less than 0.5 to 1%, then don't spend much time deciding between different fits, as it makes little difference on the final discharge. Now let's look at the options available and how you might use them to evaluate the extrapolation fit. By default, the data points for all transects in the measurement are plotted in the graph, along with the associated medians and fit. The points plotted can be changed to an individual transect by clicking the transect name in the fit parameters table. The points plotted can be changed to an individual transect by clicking the transect name in the fit parameters table. To see the medians and fit for each transect, you can use the checkboxes below the plot. Note that the fits are color-coded so that the transects moving from left to right are magenta, those moving from right to left are blue. This allows the user to identify any directional bias in the profiles. For this measurement, it appears that a constant no-slip fit were selected for each of the individual transects. However, when all the transects were combined into the full measurement, a power fit was selected. It is often helpful when evaluating the top of the profile to use the checkbox for surface cells. When checked, the top cell in each ensemble will be highlighted in cyan color. Note that the top cell is not necessarily the top cell when the depths are normalized. They may be the same distance from the water surface, but they are different distances from the stream bed, which is represented by the normalized z on the y-axis. So the surface cells lower on the graph would be representative of shallow depths. Looking over at our discharge sensitivity table, we can see that a power with a 0.1254 exponent was selected automatically by the algorithms, and this is indicated by the bold row in our discharge sensitivity table. One of the easiest ways to compare fits is to simply click on a different row in the table. So let's try constant no slip with a customized exponent. When we click on that row, two things happen. Our fit changes from automatic to manual, and we get an additional row in our table. If we select a manual fit, either by clicking in the table or by simply setting this to manual and setting the top, bottom, and exponent, we will get an additional row in the table indicating that this is a manually selected fit. It will be the bottom row, and it will be in a bold typeface. Looking at this particular selection, it looks like a pretty decent fit as well, even though it makes almost a 3% difference from what was automatically selected. This is where the user might use some of the knowledge they have at the site. Was the wind blowing upstream? Does that justify a lower velocity at the surface than that which was computed automatically with a power fit, where the velocity at the surface would actually continue to increase from the measured cell rather than decrease when wind is blowing upstream? We also recall that when we looked at the fits for the individual transects, they were all constant no slip. So perhaps constant no slip is in fact a good fit for us. One of the other things that we could look at is to look at the data used for the extrap fitting. It is now set to automatic. What that means is 100% of the data are used, and that threshold we talked about for these lower points are set to 20%. We can change that to manual, which would allow us to change the type from discharge to velocity. However, for moving boat measurements, it is always recommended that you use discharge. Then we have the option to subsection. This allows us to set a percentage of the discharge from the left bank and from the right bank that we are not going to consider. So if we wanted to look at, say, the middle 80% of our discharge, we could type in 10:90, which says go from the left bank until you hit 10% of the discharge, ignore that data, go all the way over till you hit 90% of the discharge and ignore the rest of the data, so that we're looking at the middle 80% of our data. When we do that, we once again get a constant no slip. One of the other things we see is where before we had over 1,000 points, we now have only 300 or 400, indicating that a lot of the data that was collected either in the overbank or near bank areas and accounted for very little of the discharge. If we wanted to see how the original automatic fit compares to the 80% data that we have here, we can select from automatic to manual. We can select power. We start at the bottom, and then power at the top. And our original exponent was 0.1245. The fit looks pretty good at the top, but seems to deviate some from our data at the bottom. And if we look at the comparisons again, depending on constant no-slip, now we're seeing almost 5% difference in the automatic fit using 80% of the data and the automatic fit using 100% of our data. This is actually rather rare. Typically, we find that when we change the subsection, the fit typically doesn't change a lot. I believe for this measurement, the reason for this change is the fact, as you recall, we had this really weedy vegetation, large overbank area on the left and a smaller one on the right. So a lot of data were collected on the left and right banks. Therefore, in an unusual situation like this, it might be reasonable to say, I am in fact going to narrow my data. I'll go back to my automatic fit. And let's remember that's constant no slip with a 0.364 exponent. We could go back to our automated data and now let's pick manual with constant no slip and an exponent of 0.364. And again, we see a 5% difference from our automatically selected value, about a 2% from the constant no slip using all of the data. So this is a decision that has to be made, and we can see that this bottom does tend to fit these red points, which were probably collected in the overbank area, a little bit better, but yet it doesn't fit the whole profile as well. It's really shows a lot of drag at the bottom. But with vegetation in the overbank, that is perhaps what in fact was there. So in this situation, it's one of those where we're going to have to make a decision, and our decision is going to affect our discharge substantially. In this unusual case, personally, I would be inclined to go automatic and I would go here, and I might even look at what happens if I only go 5% each side. That comes up very close to what we did with 10% each side. So that suggests to me that overbank area where there's not a lot of discharge, but there are a lot of data points, is having a substantial influence on our selected extrapolation. I believe after this evaluation, I personally would probably leave the automatic method on, but use the manual method for determining what data I'm using, and I'd probably use the 5 and 95 so that I'm eliminating the influence from these overbank areas, which are not contributing a lot of discharge, but are contributing a lot of data points that are affecting the automated extrapolation methods in QRevInt. Let's go back to automatic to get all of our data back. Then let's go manual. And let's see if we can eliminate this point with our median being almost 1,000, roughly. We probably have to go to almost 60% here. So if we typed in 60%, which is really a high unreasonable value in my opinion, we now see that that third point gets marked in red, which is this 576 points at 0.2271. That value is unreasonable. I wouldn't normally make that change. I did it here just to show the example. And again, for this rather unusual case, I would probably set 5 and 95, and then I would use the automatic fit. And I might downgrade the measurement when we look at uncertainty, because the uncertainty here is rather substantial. And finally, just to illustrate one of the other features, let's go back to everything being automatic. We need to leave the tab, come back to the tab. This box here shows the values that are set when we entered the extrapolation tab. We can change anything that we want while evaluating this data. And the final discharge is not changed until we leave the tab and click on a different tab within QRevInt. This allows us to experiment with different fits, different data subsectioning as we did. And if we decide that, well, everything we've done really isn't any better and we'd really like to just go back to what it was when we started, we could hit reset to these settings. And it would go back to whatever it was when we opened the tab. Let's go back to what we had selected. Let's leave the tab. Let's come back. And now you see that when we left the tab and we left these settings, now that becomes what is applied to our discharge. And this is the fit settings when the tab was opened. So you can play with the various settings and always go back to what they originally were when you opened the tab. Now that we've finished selecting our extrapolation, let's look at the Edges tab. Perhaps the first thing you notice is that the left distance has some caution colors in the various transects. If we hold our cursor on that cell, we see that we have excessive boat movement. So before we look at the rest of the Edges tab, let's look at the quality checks that are applied to the edges. A caution is reported if the discharge in the edge is greater than 5% of the total discharge, if the edge discharge sign is not consistent, if the boat movement is greater than 5% of the distance made good or greater than the edge distance, if the invalid ensembles are greater than 25%. A warning alert is reported if the discharge is equal to 0 or the edge type is inconsistent. The edge table allows us to change a lot of settings. First, we can change the start edge if that was entered wrong in the field by clicking in the start edge column, and we could change from left to right or right to left. We can change the type of edge by clicking under the type column, and we can choose the shape, either triangular or rectangular, or if we have an irregular shape, we could put in a custom coefficient. And finally, if no shape is appropriate and we have an estimated discharge for the edge, the user can enter that directly. These changes can be applied to all transects or only the selected transect. The same dialog can be reached by clicking in the coefficient column or the discharge column. The user can edit the left edge distance by clicking in the distance column and change the number of ensembles used for the edge computations by clicking under the number valid column, and this would allow the user to change the number of ensembles that are considered in computing the mean velocity and the mean depth used in the edge computations. The columns for the right edge are identical to the columns for the left edge as far as opening a dialog and making a change to the right edge. Below the table are two sets of graphs, one for the left bank and one for the right bank. There is a color contour plot showing the velocities and depth for the ensembles selected for use in the edge computations, and also a ship track of the boat movement for those ensembles selected for the edge computation. Clicking in the table on the file name will change those graphs. We can see in some of the graphs that the water mode changed, causing a change in cell size that in this case is rather substantial. That concludes our discussion of the Extrap and Edges tabs.